what we did last week, right? We were working on several aspects. We looked at natural polymers and synthetic polymers, artificial polymers. Out of that, natural polymers, you can divide this into two categories, mainly proteins and natural rubber. Natural rubber, they are isoprene units. These isoprene units polymerize themselves to form cis isoprene. They have a cis structure, right? Cis structure, and there is some kind of elasticity to this, but it is not totally elastic. Sometimes when you apply a force and then you release it, and you realize that they slide on top of each other. When they slide on top of each other, what would happen? You would see that the dimensions change, and that is not a good form of rubber. It's not a good final product. That is why we use a method called vulcanization. Add sulfur about 3%, up to 10% you can go, usually 1 to 3%, melt it, allow the cross-linking to form, and it will give you this vulcanized rubber. Vulcanized rubber, it has a higher melting point, boiling point. It has a higher hardness. It can withstand what? Wear and tear. What is it? Right? Wear and tear, and they have good properties, and that is what you have. But it is not a linear form of rubber. Rubber is not linear because of the cross-linking. We say it's a three-dimensional network kind of rubber. Then we talked about addition polymerization. In order for an addition polymerization to take place, there should be a double bond. Double bond. So this double bond at the cross, other double bonds, and you form these linear molecules. That is why they are called linear addition polymers, usually linear polymers. They don't have double bonds in the middle. So you can't do a vulcanization on them. No vulcanization. Polyethylene, they are bound to each other using very weak forces, London dispersion forces. Polyethylene means 2 carbons. Polypropylene means 3 carbons with a double bond. Polystyrene means double bond with a benzene ring. Polyvinyl chloride, double bond 1 chlorine. Teflon, double bond 4 fluorine. And we understood how to write the repeating unit, how to write the polymer, all that. But I want to look at, I think we discussed all of them, right? Right? We want to look at the properties of these addition polymers. First, we will look at that, properties of addition polymers. Then we will look at the condensation polymers, what does it mean, linear polymers and the network polymers, how to draw their structures. And then how do you improve its properties? They are the ones that we are going to look at today, right? Okay, right. So let us write down properties of addition polymers. Properties of addition polymers. Okay, properties of addition polymers. So write down the topic, properties of addition polymers. What are the properties of addition polymers? What are their properties? First thing that you understand is this. These are all linear polymers, right? All are single-stranded molecules. These kinds of single-stranded molecules. You don't have any cross-linking, so they are all linear polymers. So write down the first one. They are linear polymers. These are linear polymers. They are all linear polymers. First one is that. Linear polymers, right? These polymers are second one. Next one is, they are called thermoplastic polymers. These are thermoplastic polymers, right? So write it down, thermoplastic in nature. Thermoplastic in nature. Now, what do you mean by thermoplastic polymers? Right? Thermo means temperature, right? Temperature. So idea is this, when you make these polymers, what you can do is, by increasing the temperature, raising the temperature up, you can melt the polymer, change the shape of the polymer, and you can put this into a complete new shape. That is called thermoplastic. Let us say you have a, like, one of those chairs, like, most probably this is made out of polypropylene, right, that chair. So if you don't like the chair, right, you can give it to some, like, somebody who is recycling. He will break this chair into small fragments, and what they can do is they can melt it and turn it kind of into a small piece. Take that piece, melt it again, put into a different mold and make a table out of it. So you can keep on recycling this, right? That is what is meant by thermoplastic. By applying temperature, you can melt it, change the shape of it. Thermoplastic, right? Let us write down thermoplastic. Here, it is possible to apply a higher temperature. It is possible to apply a higher temperature and melt the polymer. Apply a higher temperature and melt the polymer. Right? By placing it in a different mold, M-O-U-L-D. By placing it in a different mold, it is possible to change the shape of the, change its shape. Its shape. Clear? So there is a kind of a better chance of recycling. You can do this again and again and again. This is useful in recycling polymers. This is useful in recycling polymers. That is why, like, all these people collect these plastic, putu ganna, mesa ganna, right? All that, right? All, this is the reason. Thermoplastic in nature, right? Yeah. So it's a linear polymer, thermoplastic. Very important word. Third one, they have lower melting points, boiling points. They have lower melting points, boiling points. So lower melting points, boiling points. Their melting points, boiling points are lower. Melting points and boiling points. Why? Why do they have lower melting points, boiling points? That is because they are interacted with London dispersion forces. Look at all these compounds. We have drawn them last time. They don't have very strong functional groups. Polar functional groups are not there. Because there are no polar functional groups, not these strong functional groups, what will happen is you can separate them easily. They have weaker interactions. So you have lower melting points, boiling points. And write down